Assalamu alaikum. I would like to talk about regression analysis today for the design of experiments. This will deal with correlation and regression, including some numerical problems. Regression is a mathematical technique to find equation of variables. With this statistical procedure, a relationship can be built to quantify the response of a process or a product. For example, for energy management, we need to build an equation for degree days to forecast total electricity consumption. If we have the historical data that how much days average temperature is above 65 degrees Fahrenheit, we can estimate degree days. Then we also monitor electricity consumption and use this curve fitting method to form the mathematical model. Another example, we want to improve the efficiency of a pump motor. We install variable frequency drive. Now we want to find a relation between RPM as independent variable and torque or power as response. These trends can be plotted as observed to be linear or non-linear, where in linear relationship we formulate them similar to straight line equation, in which the relationship could be positive or negative. In this analysis, the input or independent variable is also called predictor or regressor, represented by X. On the other side, the output or dependent variable is called response, represented by Y. We use curve fitting method called least squares method for simple regression model, where the error between this fitted line is calculated and then taken sum of the squares of these deviations from real-time observed values. Curve fitting is a process of finding the best fit of the model, where we try to minimize the error, also called residuals, and it could be linear, quadratic, cubic, or even exponential. For example, there are some data points following a linear equation y equals to mx plus b, where b is the y-intercept representing the baseline of the model. We can term this baseline as the overall mean of the dataset. Now the line can be fitted in between the data points, but keep in mind that not all the residuals are only positive, as well as not all the residuals are only negative. It should be in between. Simple regression and multiple regression are the two types of regression models. With only one independent variable x, we termed it as simple regression, while for more than one independent variable, x1, x2, x3, or many more, it is termed as multiple regression. If the order of variable is 1, that is the power of x is 1, the model is called linear. Non-linear model has order more than 1, such as quadratic, having second order. Simple regression can be linear or non-linear, but there are no interactions. In multiple regression, non-linear model can also include interactions. For example, x1, x2 could be in some of the terms of the multiple regression model. So far, we know that the purpose of regression analysis is to find a relationship between variables. This can be used to predict the values as well as the strength and nature of the relationship in quantitative manner. The strength and nature of the relationship are determined by a correlation coefficient. So what is correlation? Correlation is a combination of two words in which co means together and the relation means connection. It tells us about how band of data points are close to form a relation. Value of r close to -1 shows a strong negative trend, which means as the x increases, y decreases. Close to +1 means a strong positive relationship, that is, y increases with increasing x. Closer to 0, the relationship is weaker, R equals to plus 1 is a perfect positive relationship, meaning all the data points can form a trend line with zero error. Similarly, R equals to minus 1 shows a perfect negative relationship. R equals to 0 means there is no correlation and regression model is not possible. Now in the least square method, least means to minimize and squares relate variations of errors or residues. Variance of error can be found by calculating deviation of each observation with the predicted value and then taking the sum of squares of these deviations. In this method, we try to minimize the variation of error to determine the best fit. This equation y hat equals to b naught plus b1x is used for simple linear regression. By determining each y hat at the predictor x of the observation, error is found by subtracting it from yi, that is the observed value from the experiment. The least squares method is formulated from the sum of squares of error and mathematically solved by using partial differentials. The sum of squares are differentiated and then equated to 0 to find the least squares. We won't be going into that much detail, rather we will use only the formulae. Simple linear regression model is used to model the dependence of a continuous response y on a single predictor of first order. The equation is similar to the straight line equation. Intercept shows the base value of response, that it tells that there is no effect of predictor, while the coefficient is the slope that describes that how the response changes when changing the predictor. For example, y equals 4 plus 0.5x is the equation of our model. Y equals 4 when x is 0, and if x increases by 1 unit, there is increase of 0.5 in the response. This intercept or base value is also termed as the overall mean of the dataset. Using least squares method, intercept and slope can be determined, which are given by b equals sum of product of variation in x and y, dividing it by sum of squares of variation in x, while a is the average of y minus bx of whole dataset. Multiple regression includes more than one regressor. For simplicity, we take the matrix form of dependent variable y and equate it to the multiple of matrix of coefficients beta and regressor matrix x, that is y equals to beta times x. Here the first column of matrix x is of ones, while the next column have preceding independent variables. These multiple predictors can have n number of different values which are formed in different rows, giving n number of responses with n number of coefficients. The coefficient matrix has initial element of the overall mean or beta naught and then the preceding coefficients beta 1, beta 2, beta 3 of x1, x2, x3 and other regressors. This is done this way so that when it is multiplied by a regressor matrix, the matrix dimensions are same as response matrix. The coefficient matrix can be found by taking inverse of x transpose times x and then multiplying with x transpose then y. Moving on, following data is provided for DC output from a windmill represented by yi and wind velocity x. We have to perform regression analysis and find simple linear regression model. We will first determine the slope, that is b, by calculating the sum of products and sum of squares. The sum of product is on the numerator side, which is found by multiplying the deviations of x and y. On the numerator, we find the sum of squares by squaring the deviations of each value and then taking the sum. So first we will find the sum of x values and then the sum of y values to calculate the average, which is x bar and y bar. And then we subtract it from the individual values of the regressor and then subtracting y bar from yi. Then for the numerator, we will find the products by multiplying each observation. We can do this in Excel, however, is also doable by hand. Then we square the deviations of x, that is the predictor. After that, we will find the sum of the product and sum of the squares. So these are the important values which we got by performing the analysis on wind velocity as our regressor to find the response equation of DC output from a windmill. So we divide the sum of product and sum of squares to find the slope, which is found to be 0.2411. And then we find the intercept by subtracting y bar minus b times x bar, which is found to be 1.1309. Finally, we have found by using this equation of simple linear regression model, which is y equals to a plus bx, and our equation is y equals to 0.13 plus 0.24 times x. Here the coefficient of determination is 0.8745, which means that it is a good fit and can be used to predict the DC output from the wind velocity data. R square value can be also found by squaring the coefficient of correlation. We can perform simple linear regression using Excel very easily, and I will make a tutorial on that. Here an example of total electricity consumption based on degree days. If we want to forecast degree days and calculate total electricity consumption, we can form an equation using this model. The first step is to find x bar and y bar and then subtract it from x and y individual values, then multiply to calculate the product and square the x deviations to find the square of deviation of x. Then we take the sum and then divide it to calculate the slope. And then we find the value of a using formula y bar minus bx bar. So we have our equation y equals to a plus bx using this technique. We can also use the plot command to get the fitted model, and Excel automatically generate the R square values and the regression equation. We can also do the calculation for R square by using the formula of sum of product and sum of squares. Here on the numerator of R square, we have sum of product, which is squared, and then on the denominator, we have the multiple of sum of squares of x deviation and sum of squares of y deviation. In order to perform multiple regression, for example, the electric power consumed each month by a plant is thought to be related to the average ambient temperature x1, the number of days in the month x2, the average product purity x3, and the tons of product produced x4. The past year's historical data are available and presented in the following table, which is shown on your screen. We can perform the regression by using matrix method. First, we form the matrix of response. Here we just have one column where the values are arranged 240, 236, 270 until 261. Similarly, we can write an unknown matrix of coefficients starting from overall mean beta naught and then beta 1, beta 2, beta 3, beta 4 because we have 4 independent variables. But for the matrix of regressor x, we have ones on the first column. Then we arrange the values of x1 on second, x2 on third, x3 on fourth, and x4 on fifth column. We can perform this in Minitab very easily by using the command editor. I have used Minitab 17. First, I have to name the caption of the columns. I named C1 as Y, C2 as 1 for the ones of the matrix, C3 as X1, C4 as X2, C5 as X3, C6 as X4. So first, I will write the command to make a matrix of regressor, that is X, So in order to fit the values in that matrix, I will copy C2-C6 and give the space and write the name of the matrix. After that, the first step to find beta is to transpose that matrix. So I will transpose M1 and give the space to write another matrix M2. Next step is to multiply X with X transpose. So write multiply matrix M2, which is transpose of X, and then M1, which is matrix X, and then space, write a new matrix M3. After that, inverse can be found with the command inverse, and then multiply with the transpose. Now, in order to generate Y matrix, let's write copy C1 space M6. M6 is the matrix of response. Now I can multiply the previous matrix, which is X transpose X, then inverse, and then X transpose with Y by using the command multiply M5 space M6 space M7. So this M7 is the final matrix of beta, that is the coefficient matrix. So we can get the values by using command print space M7. This is the command to view the matrix. So the first value represents the overall mean, which is beta naught, and it is found to be minus 102.713. Now the coefficients, which are beta 1, beta 2, beta 3, and beta 4 for the regressors respectively, are 0.6, 8.9, 1.4, and 0.014. By this, we can find our equation of multiple regression. We don't need to perform matrix method all the time. There are functions for regression in Minitab. This can be done by navigating to stats, then regression, and then selecting response as our power, which is y, predictors as x1, x2, x3, and x4. So far we know that the total variability is equal to the sum of variability of factor and variability of error. Variability, or to say sum of squares of variations. Here we have regressors as our factors. However, the concept of levels is not applied in regression, since there is only one piece of information needed to determine the coefficient. Therefore, the degree of freedom is taken as 1 for each regressor. The method is the same. We describe the hypothesis that there is no relationship, which is called null hypothesis. Also, alternative hypothesis is defined considering there is some relationship. S's of regressors are formulated by taking sum of squares of deviation between regression model and overall mean. Total sum of squares is computed from all data and overall mean. Sum of squares of error includes the deviation of uncertainty. So we cannot find it directly, but we can find by subtracting the SS of regressor from SS total. Then mean square is calculated by dividing respective SS with degree of freedom. F values can be found by taking ratio of mean squares of regressors and error. Another method of p-value is used to conclude our hypothesis. If it is less than alpha, that is 5% usually, we reject null hypothesis, which means that there is some relationship. Since we know that R square is measure of goodness of the fit, the data point close to the trend line fitted value, if we have value close to 100%. The coefficient of determination, or R square, can be equated by taking the ratio of SS regressor and SS total, or 1 minus SS error upon SS total. R square is considered good if we have 80% or more value. We can make R square better by adding more terms. For example, interaction of x1, x2, x3, x4, or higher order of x1, x2, x3, and x4. There is also an adjusted R squared. Adjusted R squared deals with additional independent variables k rather than total observations n. The adjusted R square always have a lower value. When k equals to 1, adjusted R square equals to R square. The adjusted R square accounts for the number of parameters fit. When R square and adjusted R square are close, when the R square is probably accurate. because it means there are enough data points to calculate regression accurately. However, if they are higher, then it means the data points are not enough. Let's say you are comparing a model with 5 independent variables to a model with 1 variable, and the 5 variable model has a higher R squared. Is the model with 5 variables actually a better model, or does it just have more variables? To determine this, just compare the adjusted R square values. The adjusted R squared values adjust for the number of terms in the model. Importantly, its value increases only when the new term improves the model fit more than expected by chance alone. The adjusted R square value actually decreases when the term does not improve the model fit by a sufficient amount. So from this Minitab software, we can get our regression equation directly, which is shown on the screen. We can add more terms to make our model better by increasing the R square values. For example, adding an interaction, we can add a term x1 times x2 multiplied with the coefficient represented as beta subscript 1, 2. Also, we can add some higher order terms. For simple linear model, we have y equals to beta naught plus beta 1 times x. But for the multiple linear model, we have y equals to beta naught plus beta 1 x1 plus beta 2 x2, and this goes on. We can increase the power for our simple model and it will be non-linear, and it can be beta 2 times x squared beta 3 times x cubed. However, for multiple non-linear model, if we take the square of x2, we have to write beta subscript 2 2. Similarly, if we take the power 3, we have to write beta 2 2 2, that is 3 times. So thank you for listening. If you have any questions, you may drop your queries in the comment below. Allah Hafiz.